add up to 12.
Right. So, right. So this was, right, you did this on, for vertices in section 9.3,
Yeah.
and now you're doing it for edge. This is the one for edges. This is what you're doing in 9.4, right? Right. So,
It's also in, I think it's also in 9.3. It's just problem 7 refers back to the one about vertices.
oh, okay. Yeah.
They're both in the same section. I just was confused on how to like label edges and describe those reflections and stuff. So
Right. So then what are you supposed to do with this? Just give the,
I think it just asks for the M colorings of the edges.
oh, okay, which you can just get immediately, right? By plugging in an M equal to all those variables, right?
Yeah.
Yeah.
Yep. Makes sense.
Yeah. Cool.
Thank you.
Yep. There was one that Logan was asking me about where he was wanting to, did they tell you to, right, so in 9.4, didn't they have you do like some of these same shapes where you had to give a pattern inventory or something?
Yeah.
Yeah.
Mm,
And pattern inventory for how many colors?
2 colors.
And so did they have you do that for this one?
I don't remember which part it was. Yeah.
I might have, because I think I just said, as we already determined, and then just
Yeah.
plug stuff into.
Same shapes. Or the same.
Right, so you would just go like this, right? So it'd be, and then it would be b to the 6th plus w to the 6th. Right, and you would plug this thing in here, so this would be a 12th. Right, and it would be b plus w to the power 12 plus 2b to the 6th plus w to the 6th squared plus 2b cubed plus w cubed to the 4th plus b squared plus w squared. By the way, when you think about this enough, it makes total sense that you would be replacing like x sub I with b to the I plus w to the I, because x sub I represents an I cycle. And the minute that you color something one color, you have to color them all that color if you want them to be fixed by that particular permutation. Yes? And I mean, in the lecture, I've been trying to articulate that in more of an algebraic fashion. And I mean, I wrote out the full gory details in the notes finally, because I couldn't leave it undone, okay? I mean, they don't do that in the book. They just do it for like, it's really example driven. But, you know, I'm gonna finish that off tomorrow very briefly. But so then it's like 6 times b plus w squared times b squared plus w squared to the 5th. Do they ask you to extract any like coefficients or anything?
Not on that one.
No.
Okay. Now, like this one isn't so obnoxious. Like you could actually extract coefficients by hand on this one, because all of these are just binomials. Do you know what I'm saying? Like you could, like if I asked you for the number of colorings that have, you know, I have 12 edges. So if I wanted to know the number of colorings that have 6 black and 6 white is, then I would just have to extract the coefficient of b to the 6, w to the 6 from this thing, yeah? And that would actually be very doable because you know the binomial theorem. So yeah.
Cool.
In fact, you know, I can't, oh, how do I do this? Okay, so if I want to do, like if I did this, right? Okay, so b to the 6th, w to the 6th. That is the number of distinct, truly distinct colorings under the edges of this object under the action of G. I would have to extract that from this thing. Right? What would that be? Well, it would be a 12th times something. A 12th times what? Well, what about that B? What about B plus W to the 6th? Would that contribute anything? What about B plus W to the 6th? Would that contribute anything to B to the 6th? Would there be anything that would have a B to the 6th, W to the 6th in it? What do you think? Because this would involve the binomial theorem. You would go like 12, choose 0, B to the 12th, W to the 0, plus choose 1, you know, B to the 11th, W to the 1, etc. Remember, like if I were to expand this B plus W to the 12th out. So I think that there would be a 12, choose 6 coming from that. Yeah? Because that would give me a B to the 6th, W to the 6th. From this guy, is there anything? Is there anything that I would get from that?
Wouldn't you get to choose one from that one?
Which one?
Well, you'd have that 2, and then aren't you going to have another factor of 2?
Okay, so, right, it'd be B to the 12th, and then B to the 6th, W to the 6th,
Mm-hmm.
and then W to the 12th. You would square this out. So you're saying you would get a 4, right?
Yeah.
Something?
Yep.
When you square that out? Oh, thank you. Okay.
Nice.
Play with my little toys all the time. Here's the cube right here. Okay. So what about the next one? What about the next summand? Be B to the 12th. So it'd be 4, choose 0, B to the 12th, plus 4, choose 1, B to the 9th, W to the 3rd, plus 4, choose 2, B to the 6th, W to the 6th. So it'd be 2 times 4, choose 2. Kind of see what I'm doing? I'm just thinking about expanding these things using the binomial theorem. Okay, so these guys are giving rise to these. Okay, what about the next one? What about the B squared plus W squared raised to the power 6?
Would it be 6, choose 3?
Yes. Right, because then that would be B to the squared to the 3rd and W squared to the 3rd, which is B to the 6th, W to the 6th. Plus, what's the next one, Cassie?
6 times. Oh shoot, we have 2. Is that B plus W squared times that?
Oh, yeah, yeah. Oop.
Oh, I'm not sure.
What about there's a BW term from squaring B plus W, right? There's a BW term from squaring B plus W. That's not going to help because all of the powers of B squared, W squared are going to be even. Does that make sense?
Mm-hmm.
So I can't be like doing BW and bumping that up. That can't get me to B to the 6th, W to the 6th.
Yeah.
The only ones that are going to be possible are, you know, B squared from the first thing. And then I would have to have B to the 4th, W to the 6th. from the second thing, b to the fourth, w to the sixth from the second thing. How would I get b to the fourth, w to the sixth from the second thing? Wouldn't that be 5 choose 2? But then I also have 6 times, I could have done it the other way around. So b to the fourth, w to the sixth, but I also could have done w to the fourth, b to the sixth. So that's also 6 times 5 choose 2. And there it is. We actually were able to compute this thing by hand for this one because we know the binomial theorem. You just kind of write it out. You'll see how to actually extract some of these in simple cases like this, okay? So you don't have to resort to using Wolfram alpha in some cases, okay? Hopefully that kind of makes sense. We're just using the binomial theorem, okay? I'm not doing any kind of magical incantation or something right here. All I'm doing is thinking about the binomial theorem, okay? That's amazing. So that's the number of 6 black, 6 white edge, truly distinct shapes arising from this thing, okay? All right. What else? Other questions? What other questions are there?
I'm still trying to, I don't know if you can hear me, but I'm still trying to, I guess, completely wrap my head around why, okay, so like when we're plugging in b plus w's, when you plug in the 1 for x1, obviously that's just b to the 1 plus w to the 1. And it always corresponds to like the length of the cycle that you're talking about, which I kind of get like, just like common sense wise why that would be, but I'm trying to, like when you derived it a few lectures ago or a couple lectures ago, I was a little bit lost because I was rewatching them just to help with the homework and stuff like that, and I'm trying to realize how that like exactly why we have to do that in terms of like the coefficients and stuff like that, which I think, and I know you were just hitting on that a little bit, but I don't know, I guess I'm still having a little trouble understanding like exactly why that is, because it seems like I don't know, just in my head, like when I was first watching it, it's like you have your b and the w, and then you're seeing all the ways that they can be combined, and you're like adding up all the different ways from all the different terms and stuff, but for some reason I'm not quite picking up on why you have to space it out a certain way with those exponents.
Space it, you mean, what do you mean space it out, I guess?
Okay, well, because in the video you said like, oh, well, we're gonna, instead of doing b plus w again for a2, we want it to be b squared plus w squared, so that the powers are increasing or decreasing by 2 each time rather than by 1 each time. And I don't know, for some reason I'm having a little trouble
Well,
understanding.
because the reason you do that, Paul, is if I color again, we're looking at we're kind of dealing with the term that has to do with asking the question, how many colorings are fixed by pi? Yes? How many colorings are fixed by pi? Because that's the term in Burnside's theorem, yes?
Mm-hmm.
And if I want to actually encode that, I have to think, all right, if I decide to choose a particular 2 cycle and color a vertex in the 2 cycle black, well, then what am I going to be required to do, Paul, with the other vertex in that 2 cycle?
Oh, well, it would also have to be black.
Right. So how many total vertices did I color? Black.
You colored 2.
Yeah.
By picking 1, you've essentially colored 2, I guess.
Yeah, that's exactly right. So that's why it makes sense that it would be a b squared instead of just, because b squared means how many vertices are colored black.
Oh, right. Okay. So I think, okay, that makes sense. I think the thing that was confusing me is I keep wanting to associate B and W as like somehow that's like that's gonna be like the number of like a certain color that we
No.
have. But really, I guess those are really more like placeholders, and then the
Yeah.
exponents and coefficients are the only thing we care about.
Yeah, that's exactly right. It's exactly
Okay.
what we did with generating functions. X was sort of meaningless to us.
Right.
A placeholder, it was a variable. Same thing is going on with B and W. The only reason we
Okay.
use B is it just reminds us of black. And the only reason we use W is it reminds us of white.
Mhm.
So, okay, why in the world would I plug in B cubed plus W cubed for a 3 cycle? Well, again, when our concern is figuring out how many colorings are fixed by pi, if I color one vertex in a 3 cycle black, I need to color them all black. And once I choose black for that cycle, I've used up 3 vertices, which is why I use B cubed, right? So it's B cubed or W cubed, which is why it's plus, okay?
Gotcha.
And that's kind of the intuition behind what's going on.
Hmm.
It's easy. The weird thing about this is it's sort of, once you have it in your mind, you're like, oh yeah, that makes sense. But then when you actually go to try to write it out, it ends up being fairly fierce.
Mhm.
I mean, you have just a multinomial nightmare. Okay. And what I'm trying to do is at least give it to you in a way that's digestible. And that's what I did in the very last lecture. And again, I'll kind of go through the ultimate formula in like 15 or 20 minutes for Thursday's mini lecture. But yeah, it's all there. It kind of makes intuitive sense when you think about it this way. So does it make sense to you, Paul, then, that if I had like a third color in here, I mean, that would just be, plus R, or, plus R squared, or plus R cubed, etc., right?
Yeah, that makes sense. I think okay. So like in the 3 case, let's just say just for the sake of argument, so keeping it in B cubed plus W cubed. In terms of the coefficients, like your A3 choose whatever. The reason why, in a sense, we want them to be increasing or decreasing by 3 is because there is going to be no in between, because
Yeah.
as soon as you've picked a group of 3, or a cycle of 3 rather, you have to fill up that whole thing.
Yeah. And if I
Okay.
pick two 3 cycles, Paul, if I pick 2 3 cycles, then how many things am I going to be coloring black?
If you put one black in one 3 cycle and one thing in another 3 cycle,
Yeah,
and one
yeah.
black in another 3 cycle, well then you're coloring 6 blacks at
Yeah,
least.
right. So which is B cubed squared. Or if I
Right.
do a B, if I pick a 3 cycle to color black and another color white, it's going to be basically a B cubed and a W cubed. Yeah.
Okay.
So all of the math is being done in the exponents, just like has always been the case with our
Generating functions.
generating
Right,
functions, and then the total count is tracked by the coefficients.
Gotcha. Okay, that helps a lot.
It's a miracle, right?
Yeah.
But it works.
When we learned about the cycle index polynomial, I think that was the one where like the first time I saw it, I was just immediately like, wow, that's really cool. This one, I was like, as soon as you said like, now we can not only do that, but we can also find out how many of a certain like any combination of colors. I was like, oh man, that's gonna be insanely difficult. But then once we actually got the formula, it wasn't that difficult. But I just wanted to make sure I understood all the math behind how we got there, basically.
Yeah.
But that makes
Yeah.
sense.
Yeah.
But that is really cool though.
Yeah. All right. Good question. What else? Like we have a non-video participant in here. Who's it? Oh, that's me. Why do I always do that? Okay. Okay. That's literally like probably the 20th time I've done that since we've gone to this format, but yeah. Always wanting to make sure that everybody's getting their questions answered. Okay. What else? Anything else? So if you haven't downloaded the combinatorics notes, I think the last update was less than an hour ago. So That's one of the problems with kind of sending you out the combinatorics notes, as I'm constantly changing them. So the new ones are up there. And there are some incredible formulas. Like, here, I'll show you the ultimate thing here, and then we'll be done, I guess. So this is the ultimate formula down here. See if I can put this in a view that's less obnoxious than this teensy thing. Oh, by the way, I pasted, I don't know if you saw this, but I actually pasted a link to the Wolfram Alpha syntactic input of this stuff. You can actually click on that and it'll take you directly to that. Okay. And I did a couple things, other things I said I would do in there. I do the count, there's that. And then you know that when you have a giant gap like this in a file that you're about to get something huge. So here it is right here. Okay. So this is the actual multinomial expansion of this thing. And these sums are incredibly complicated, but this is a legitimate sort of shorthand way of writing them. There's really like tons of sums in here or whatever. But the main point is you see these factors right here, and that's exactly what we had up here when we were counting stuff. We ended up with this, okay? So that kind of verifies that this is indeed giving us exactly what we would want. Okay, so this is a giant exercise in multinomial prowess. Okay, so there you go. That's the shorthand. Yeah, right. That is the shorthand. The longhand would be awful. Okay, so all right. Is that all your questions? All right. Well, hey, thanks for stopping by. Appreciate
Thank you.
it.
Thanks, Dr. Hammett.
All right. Have a good afternoon.
You too.
You too.